In the last lecture, we were talking about the figures of merit, and we left it at limits of detection. We had just finished defining qualitatively and quantitatively what is limit of detection and what is limit of quantification. Now, you're going to find in the literature that some authors define limit of quantification and LOD in terms of signal to noise. And this is not necessarily, off, but it's sort of loosely, a definition of the same limits of detection and limits of quantification. So it's good you understand, what the authors mean, when they talk about signal to noise as a way to define the LOD. I think, remember, we used this relationship previously to calculate the LOD, signal of the blank, plus 3 times standard deviation of the blank. But you would find in some literature, the signal to noise is equals to 3, as a definition for the limit of detection, which you can see is not necessarily wrong, so that is a signal of the blank. And this is the signal of the analyte, and you can see the height of that minus the height of that, is equals to 3, which is very similar, to what you have in this relationship. Whereas the limit of quantification, in this kind of a way to express it, the signal to noise, should be equals to 10, meaning, the signal, of the analyte should be 10 times larger, than the signal of the noise. And remember, the signal of the noise, refers to the signal of the blank. Remember that. So when you're running the blank, wherever you're getting, it's actually the signal of the blank, which is noise, which is the definition really of what noise is. So take note of these kind of similar definitions, for limits of detection and limit of quantification. You'll also find in the literature, people talking about reporting limit. And this is a concentration below which the regulatory bodies say the analyte is not present. For example, you take a product, in this case maybe a lipids or a fat product, and you see sort of these are the nutritional facts. And then they indicate, in this case, for example, there's only 0 grams of trans fat. Now, this is the reporting limit. It doesn't mean the trans fat is completely not there. It just means using the analytical method they chose, it's much below the limit of quantification. Maybe somewhere in the limit of detection, but you cannot reliably, quantify it. So the reporting limit, is set at least, 10 to 5 times higher than the limit of detection, So accuracy, again, we've talked about this as a nearness to the truth, and I think we earlier talked about it, and you easily calculate it, using this simple relationship. You've determined using the analytical method what the concentration is minus, what the true value is. And we already discussed with you, how to determine the true value. And you determine the true value, by analyzing, the sample many times. Hopefully, by different types of instrumentation and by different type of people. So if you realize, there is a bias, then there is a problem with the accuracy, and we already said this before, that this can be detected or can be corrected, using calibration, for example, because it's a systematic error. Precision, on the other hand, refers to the reproducibility, of your data. And quantitatively, you calculate this. We've done it before using absolute standard deviation. And you can also, calculate it using variance, or you can use, the relative standard deviation, which you've already come across before. or even the standard error of the mean, which is absolute deviation, divided by the root of the number of measurements. Now take note of this, and this is important, all right, that as the concentration decreases, your standard deviation increases. You can see, and this is what they call the Howin's trumpet. As you get very close to the limit of detection, then your standard deviation becomes so high, and that way, you lose the ability to confidently quantify your analyte. And so that's why, we talked about the limit of detection. Often, when you're doing the reporting limit, the reporting limit, should be somewhere around the limit of quantification or higher, because the limit of detection, is very, very erratic, because of the standard deviation. Okay, so this is important, that as the concentration decreases, the standard deviation increases. And you're going to see this in the lab too. As you run the blank, you're going to see the standard deviation of the blank, sometimes it's very close to 100%, because, it's very, very erratic. It's very, very erratic. So types of precision, and again, remember, precision, we are using it to quantify, reproducibility. And reproducibility, is a figure of merit. So there are types of precision out there. And, you can have instrument precision, so that's a variability, within the instrument. And every instrument, has got different levels of variabilities, of precision. Give you an example, and you've already seen this with a pH electrode potentiometry. It tends to be very, very erratic, and you get to use it. On the other hand, you've got some analytical instrumentation, that are very, very, very precise, like coulometry. Coulometry, a very, very precise technique. Another good example, mass spectrometer. It's very, very sensitive, but it's got a lot of imprecision, meaning it's very, very variable. Now, you also have another type of precision, called the intra-assay precision. And so this refers to, a situation when you analyze, the aliquot of a homogeneous material several times, by the same technician in one day, using the same equipment. So you can see it's not a very robust, method of determining, precision, because you take a homogeneous sample and then you run it many times on the single day using the same instrument. Now, a much more robust, method of determining precision is what they call the ruggedness or intermediate precision. And so this is where you take an assay, all right, and then you get multiple technicians, to analyze that assay using different instrumentations, but you do it, in the same lab, but you do it in different days. So you can see it's a bit more robust. So you do it in the same lab, but different technicians, are running that assay using different instrumentation. Now, the last type of precision, which is the most robust, is a so-called interlaboratory precision, which is very similar to the intermediate precision. The only difference is, you take the assay and you get different people in different labs analyzing, that assay. And you would wonder what's the purpose of doing this? So the purpose of doing this is to actually validate analytical methods. So analytical methods, are validated, especially, by checking the robustness, by analyzing, by having different technicians in different labs, analyze that particular assay. So robustness is another figure of merit. If you develop an analytical method, you want to assess how robust it is. And robustness means, the ability of your method to not get affected by small changes, in in the lab. So the changes could be, you know, things like pH. The changes can be temperature. You know, the changes can be, you know, humidity and so on. So you want the analytical lab, rather method, not to be prone to be affected, you know, by small variations, you know, within the lab. And that way you would know if that method is very robust, and that way it can be used in different geographical locations. Now, the other figure of merit, you know, is the so-called specificity. Sometimes people call it selectivity. And so this is the ability of the analytical method to be very, very specific, you know, to analyze, you know, the analyte while being completely blind to the metrics, okay? And you quantitatively, you know, measure it using what they call selectivity coefficient, where you get the slope, you know, of the analyte. Sorry, you get the slope of the interfering species, the B, divided by the slope, you know, of the analyte. And if the selectivity coefficient, you know, ideally, you know, it should be very, very close, you know, to 0, because the instrument method, you know, should be almost blind, you know, to the B, and very, very selective to the A. So the ratio is such that the selectivity coefficient should be very close, you know, to 0. Okay. Now take note of this. Ideally, when you're dealing with sensors, this is where you really need to determine this particular figure of merit, you know, selectivity. For example, the pH electrode, you know, which is an ion selective electrode, you want it to be very specific, you know, to the hydronium ion, and to be completely blind, you know, to the other types of ions. Of course, you know, in real life, you know, that doesn't happen. You know, almost any sensor tends also to pick up or to be affected, you know, by the matrices, but ideally you want that not to happen, or you want that to happen in very, very limited cases. So you can see again, the goal here, you know, is to handle, you know, the matrix effects, which we call the big analytical challenge, because every sample always has got the matrices that tends to interfere with the analysis, okay? And so that's why you would use sensors, you know, that are very, very specific or selective, you know, to the analyte of interest. Now, in the event, you know, you don't have sensors, you know, remember, you can equally mitigate matrix effects using other methods. And I think you guys already know this. You can mitigate using extraction. We've already talked about it. Using separation, using things like crystallization, you know, just getting methods of isolating your analyte of interest. But remember that it always takes time, cost in terms of solvents and so on, you know, to remove matrices, you know, from the analyte. But it's part of analytical chemistry. Other methods like derivatization can be used, you know, where you take your analyte and then you react it, you know, with a reagent, and then the product, you know, becomes very easily detectable, you know, by your analyte. You can also do what they call masking, where you take, you know, your matrix species, you react them with a reagent, and now the product is such that cannot be detected, you know, by the instrumentation, and so that way you've masked the matrices, you know, from the analyte. So the next chapter, or the next part of the chapter, you know, is to talk about calibration methods. And there are three different types of calibration methods that we're going to talk in this chapter. And, you know, the methods involves external calibration method, standard addition method, and internal standard calibration method. And we're going to talk about it, you know, in the next segment, you know, of the video lecture.